So all of you completed the quizzes, which is great. And we do have a test, right, due on Thursday. And I did do a little video. I don't know if you had a chance to look at the video. About a 15-20-minute video, just to for you to prepare yourself for the test. Okay, you just want to make sure. But don't try to test out without looking at the video. And also do a review of the topics for the test that I talk about in the video. Make sure you do that before you take the test also. Don't wait till the last minute to take this test. You know, even though the topics aren't difficult, I would say the test itself, I would say, is moderately difficult because you have the open book, right? It's an open book test. So, but I did want to make sure that you're prepared and you know what to expect when you take the test. It is 75 minutes long, as I mentioned, and 17 questions. 16 of them are multiple choice, the first 16 of them, worth 6 points apiece, so it's 96 points. And then the last question, number 17, has 2 parts to it, and it's worth 14 points. So, but do remember that to get an A in this course, you need an 86 or above, right? And for that test, there's 10 extra credit points there. So, which I throw in there. All right. But again, look at the video because that's why I made it, so that you can know how to prepare for it. But please do prepare for it. Don't walk in cold. I mean, unless you really think you know everything really, really well. If you do, that's fine. But if you don't, there's some hesitation there, then definitely listen to the video and definitely do a review before you take the test. All right. So I think last time we were talking about, Ann, did you have a question? I don't know if
Yeah. Will the test cover chapter 1 to chapter 5?
Through chapter 4.
Oh, just for chapter 4?
Yes.
Or to chapter 4?
1 through 4. I did go through. It was the pre-recorded, right? Chapter 4 was pre-recorded.
Mm-hmm.
Didn't I pre-record chapter 4? Or did I?
I don't know.
You recorded chapter 4. It was just one of the one day that Han wasn't here.
Yeah. Yeah, I pre-recorded it.
Okay.
The question is it on chapters 1 through 4, or is it just on 4?
1 through 4.
Okay, that's what I thought. Thank you.
Yeah. Now she had mentioned, Han mentioned chapter 5. No, we're not even finished 5 yet.
Okay, I got you.
5, it will be in the second test. Not this.
Okay.
I always make sure we have completed everything and have at least some degree of a review before we take a test on the topics. 1 through 4.
Can I have another question?
Yeah, go ahead. Go ahead, Han.
Because we discussed before, we did really bad at the second quiz. So we wonder if you can release the answers.
Yeah, I can release the answers. I can actually go to, let me see if I can do it here. Maybe that would be the best thing to do. I'll go through it for maybe 5 minutes or so. So give me a second here. Let me, oops, I didn't want to do that. All right. Let me do this. Hold on a minute. Minimize. Right. Seems like when I'm recording, I can't minimize. Oh, I know what I need to do. That's so silly. All right. Give me a second here. What I'm going to do is see if I can show you the answers or tell you what the answers are just by looking at them. All right, so let's see if this will work. Not sure if it will, but I'll give it a shot. All right, see if I can share a screen with this thing here. the there we go. All right. So this is quiz number 2. Okay. Notice when I put answers down, I put multiple answers, thinking that there are other possible ways somebody could answer the question, even though this just comes right out of what we talked about. So for a negatively skewed distribution, the mode is typically greater than the median, right? That's true, right? Negatively skewed, all right? And for a positively skewed distribution, the mean is typically greater than the mode, okay? So hopefully everybody got that one. Question 2, the blank is the average of the absolute value of the differences from the mean. Well, that's the mean absolute deviation, or the MAD. There's actually 2 other, book gives you 2 other terms also, right? For that. I'm taking this like right out of the book, literally. The next one says the blank quartile has 25% of the data above it, which means there's 75% of it below it. So that is the 3rd quartile, upper quartile. You have to read this carefully. When you read these sentences, read them carefully. While the blank quartile has 25% of the data below it, that's the 1st quartile. Notice again, I gave you 3 different possible ways of answering that. The difference between these 2 quartiles is called the blank range, interquartile range, but interquartile range. All right, Q3 minus Q1. All right, question 3. The blank variance is the ratio of the sum of the squared deviations from the mean divided by the number of data values minus 1. That minus 1 tells you it's a sample variance. The blank of this variance is the standard deviation. What's a square root?
I looked at this book. It says positive square root.
Oh, all right. I'll go in and give you credit for that. Don't be that precise. Square root's good enough.
But I just follow the book.
Yeah. Well, the thing. Yeah. All right. Square root, good enough. But I'll correct that for you. All right. The box plot graphs the 5-number summary, which includes Q1, Q3. These are the 2 quartiles. The minimum value, the maximum value, and the, of course, median is the answer to that one. But I even put Q2 in case you answered that. And the next one, the blank, is the percentage of the mean. That is the standard deviation. That, of course, is the coefficient of variation, or the CV. Question 4, the blank is the number of standard deviations at data values from the mean. Well, you can write it as the z-score, the standardized value, the standard value, or the standard score. All those are correct. All right, and a blank sign indicating that the data value is greater than the mean. Well, and a blank sign indicating the data value is greater than the mean. Hold on a minute. Oops, I'm sorry. I skipped one. All right, up here. With a blank sign indicating that the data value is less than the mean, well, it's a negative sign, right? SIGN.
I have a question.
Huh?
I put a negative sign, the real negative sign. Is that correct? Like.
I want you to put words. Yeah,
Okay.
I'll give you credit for that too. I'll look through your test too, and I'll give you credit for that. But
Okay.
don't be too fancy. I don't expect you to put symbols in here. Right?
I see.
Yeah. And you put a plus sign for the other one? All right. Chebyshev's theorem states that for any distribution, there's a minimum of blank percent of the data set that's within 2 standard deviations of the mean. The answer is, anybody? 75%.
108.
75% is the answer. What percent? Blank percent. 75% of the data is within 2 standard deviations of the mean. That's Chebyshev's theorem. If it was an empirical rule, which if bell-shaped, the answer would be 95%. All right. Question 5. This is a long one, right? In blank research, the researchers relies on watching or listening. I took this right out of the book. So this is observational research. In blank research, that's experimental research, right? The researcher tries to identify cause and effect relationships between variables, blah, 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 blah. In both types of research, we can acquire participants for the study through sampling. In a blank random sample, we select participants by breaking the population into groups and then taking a simple random sample within each group. Well, that's the stratified sample. Stratified sample, random sample. However, if the participants are not randomly selected within each group, but are chosen in a non-random fashion, well, this is a non-probability one, and it's called a quota sample, right? Quota sample, the book made it clear, it looks like a stratified sample. You break the population into groups, but you do not take a simple random sample within each group. You just select the people in a non-random fashion inside each group, and that's the quota random sample. Or not a random sample, quota sample, it's not random. All right.
Does it use that exact phrase quota? Because I don't
Quota.
exactly remember looking through that.
No,
Looking at the book.
no,
I'll take it from the
it's
book, sorry.
quota. Nope, that's what it is. It's exactly what it says in the book, quota. No other possibilities for that one. I was comparing it to the stratified sample. It can't be anything other than the quota sample because it mentions it in there. All right. Again, I want to make sure, the reason I give you all this, I want to make sure you're reading the book. All right, not just like skimming it or, I want to make sure you read it. So that's why I give you these. These aren't questions that have come out of footnotes or, in some weird way. These are come right out of the book and when they're describing these particular definitions. So all right, so it's definitely quota. There's nothing else like that. All the others are not quota. Way this, I was very careful how I described this. All right, let's go to the next quiz, to quiz 3. Oh, that was quiz 2, yeah. Did you want to look at quiz 1 or you're off? I thought there was a quiz 3. I'm thinking of my other course that I teach at Rowan. I had 3 quizzes for them. Quiz 1, did you want to go over it or Mo, did you need to see quiz 1?
No, I'm okay, thanks.
All right, how about anybody else? Quiz 1? I think you're all okay with quiz 1? Yeah. So I think Han, maybe I'll correct. I'll look in 3 years. Mo, did you need to look 3 years at all? Or are you okay with what you got?
I think the first question that Han mentioned, she wrote something different for that was technically right. I think it was the positive square root I also wrote, but the rest I think were just.
All right, then I'll correct that too. And Steven, you're okay, right? I can't hear you, Steve. You have your there.
That's very strange. I totally unmuted myself in the beginning, but no, my mistakes were all legitimate. So.
Okay, all right. So that's it for that. Any questions about? All right. So again, I'll look, Mo and Han. I'll go through your quiz number 2, and I'll make sure that it's all. I try to anticipate what possible variations of an answer is, but I can't always get all of them. I'm always surprised when I see other people's responses. So as long as you ask me, I will double check. All right.
Yeah.
Okay. All right. So that's it. So let's now go to what we were doing last time, which was chapter 5, right? And I want to actually complete, before we start going over the different homework type questions I think we were going through last time. I want to go over the last topic. And maybe we'll do a quick review. I think maybe that would be good. A quick review, and then we'll go over that last topic. So in the beginning, we talked about probability. And there's a probability we can look at as an experiment where an outcome of the experiment is what we're looking at, and then we repeat the outcome over and over again, just like we would do in any experiment. So an experiment means an activity or measurement that results in an outcome. Sample space is a list of all possible outcomes of a probability experiment. An event is one or more of these outcomes of the sample space, could be the entire sample space. And probability is a number between 0 and 1. That is the chance that an event can occur within that sample space. And then we talked about how we write events. You write them with capital letters like A. And using notation from mathematics, we would show that the probability of A is between 0 and 1. And the complement, hold on a minute, let me get rid of the phone here, hold on. I literally throw the phone out of the room. The phone keeps working, Yeah. Anyway, the probability of the complement of an event, the complement of an event is everything in the sample space other than event A. So we show that with A with an apostrophe. So the probability of A plus the probability of everything else that's not A is going to always be equal to 1 because it's the entire sample space, right? A and not A is the entire sample space. So the probability of the sample space is always equal to 1, which means absolutely certain to happen. And we can use algebra to say that the probability of A is equal 1 minus the probability of its complement, or the probability of its complement is equal 1 minus the probability of A. Both of these are derived from this equation here. There are 3 approaches to probability, as we went over before. The classical approach says that we can predetermine a probability by looking at the number of possible outcomes for the sample space in the denominator, and then the numerator of the probability would be the number of possible outcomes for the event. However, if we do not know ahead of time what the sample space looks like, then we most likely do the relative frequency approach, where we run an actual experiment, such as a survey. The total number of trials is your denominator, and the numerator is the number of trials in which the event occurs. And the subjective approach is what most of the people in the world use for probability, because they don't know how to do any of this. So it's just basically based on belief, right? Their own personal belief or experience. Odds, of course, is the probability of an event divided by the probability of another event, or maybe its complement. That's the odds for an event. And the odds against would be the probability of it not happening divided by the probability that it is happening. And we express odds like something like 2 to 1 or 1 to 2. That's how we usually express odds. And then if we're given the odds like 2 to 1, what we do to find the original probability is we add the two numbers, like 2 to 1 would be 2 plus 1 is 3. We put that in the denominator, and then we put in the numerator the actual the first number. If it's well, if it's 2 to 1, it would be 2 in the numerator, and if it's odds against, it would be 1 in the numerator. We'll do an example. We'll do examples like that. Addition rules. This is this one here is the general addition rule. Remember, the U here means union, or we use the word or. So in general, when we add, or when we say the probability of A or B, it's a probability of A plus the probability of B plus minus the probability of A and B. If the two events are mutually exclusive, then the probability of A and B is 0, and we're left with the simple sum of the two probabilities. With the multiplication rule, in general, the probability of A and B can be one of two possible probabilities. or it's a multiplication rule, so it's two possible multiplications. It's either the probability of A given B times the probability of B, or the probability of B given A times the probability of A. One of these two is correct. If A and B are independent, then these probabilities here, which are conditional probabilities, become unconditional probabilities. In other words, if A and B are independent, the probability of A given B is equal to the probability of A, and we end up with this. And down here, the probability of B given A will become the probability of B, and it'll be probability of B times probability of A, which is, of course, is the same thing as this. So if two events are independent, which means one event does not affect the probability of the other one, then we simply multiply their individual probabilities. And of course, here's the formulas for conditional probabilities. When we write it this way, the probabilities of A and B are considered marginal probabilities, and the numerators here are the joint probabilities. Bayes' theorem is just is derived from a conditional probability, like this one here. Okay, it's equal to this. That's the conditional probability formula. But then, if we want to calculate the probability of B given A, and we're only given the reverse, the probability of A given B, then we can use Bayes' theorem to actually calculate this one right here. If we're given this one, A given B, and we want to find B given A, then we use Bayes' theorem to do that. So the numerator becomes the product rule, right? And the denominator, we list all the possible probabilities of A in this case here. Right? Now I only have two of them listed here, right? The probability of A given B times the probability of B. And notice I say the probability of A given not B times the probability of not B, but you could have multiple sums in the denominator if we happen to know that there are three possible answers or four. All right. And I think I showed you an example last time with the machines where there were three machines, right? So it would be three terms in the denominator. And then I think I went through page 139, the answers to these questions last time. So I'm going to skip the answers for now, and I want to go to the very last topic, which is permutations and combinations. Let's actually go to the book. We'll go to the textbook. And where are you, textbook? See it. So give me a second here. I don't know. If I click that, it probably will show up now. Yes, this is it right here. All right. This is the last section of chapter 5. Now, sometimes in introductory classes, at least in Camden County, if you were taking the Math 111 course, you would not be covering this particular topic. And I think it's because some people, not me, but some people in some math departments feel like this is too advanced for some people to do, but I don't think it is. And I think it helps explain probability a little bit. And I think people struggle a little with probability if they don't have this part explained. Now, let's just go back to the notes just for a second, because I want to tie two topics together. So go back to the notes. Okay, now, the classical approach to probability. The numerator and denominator says number of possible outcomes, right? Now, this is predetermined before you even run an experiment. You can do this, right? If you flip a coin 10 times, right? We can count the number of possible outcomes, all right? Roll a dice 2 or 3 times. We can count the number of outcomes. Sometimes, so the number of outcomes, you're literally counting, aren't you? You're literally doing what you did in grade school, right? Elementary school, you learn how to count, right? 1, 2, 3, 4, 5, right? Well, some sample spaces are big. And if you tried to list all of the possible outcomes of the sample space, you would be sitting and counting for a very, very, very long time. Let me give you an example. Are you all familiar with playing cards? Cards in a deck of playing cards. You're all familiar. All right. You know there's 52 cards. Now, just a little side note, probability was developed in like the 16th century, I believe, or maybe the 17th century, I don't know, somewhere around that time, because there were gamblers in Europe, and they hired mathematicians to come up with the odds or probability of them winning certain games of chance, right? That's how it got developed. And who did they hire? They hired religious monks, literally religious people who were spending all of their time, well, most of the time praying, but then the rest of the time, many of them took up scientific endeavors, right? Gregor Mendel, who's the father of genetics, was a Christian monk. And many of the earlier mathematicians were religious people who that's what they studied. They studied mathematics. So they're the ones who developed probability, at least in the beginning days. Anyway, games of chance were the original reason why probability got developed. It's crazy, but that's the story. So it's not a bad idea to use a game of chance, like using playing cards, as an example of how counting works, right? I don't know if you ever saw the movie Rain Man, but Dustin Hoffman, who plays Rain Man, was very good at counting, right? So when they got to I don't know if you saw the movie, but when they got to Las Vegas, that's what he did. He bragged about counting cards. But counting is all about calculating these probabilities ahead of time. The problem is we can't all be like Rain Man. We can't just count, huge sums. We have to sometimes have formulas for counting when the number of things that we count are large. So what were developed were these formulas. And that is what the last topic is here. Permutations and combinations. So an example of a permutation. Let me give you an example of that. If we had a race with 8 people in a race, it could be swimming, it could be a running race, whatever it might be. And there's 3 of them will get a medal, all right? And we want to know how many possible first, second, and third place winners will there be, where the order does matter. It matters who's in first, who's in second, who's in third, all right? The order matters. Well, if you think about it, 8 people could possibly come in first, right? Out of the 8 runners or swimmers, 8 people, all 8 of them could end up in first. So 8 is the number of possible first place finishes. For second place finishes, once somebody's finished first, that person is now gone. They're not part of the remaining group. There's only 7 left. So there's 7 who can possibly finish second. And then for third, there's 2 people now finish first and second. For third, there are 6 left. And what we say is 8 for first place, and 7 are available for second place, and 6 are available for third place, which means it's 8 times 7 times 6, it's the multiplication rule. And they're independent events, aren't they? Finishing first, you can't finish in first, right? They're independent. Finishing, right? Independent events, you multiply them. Okay? Finishing first has nothing to do with finishing second, and it has nothing to do with finishing third, all right? So you 8 times 7 times 6 are the total number of possible finishes when order matters. When first, it has to be first, second, third. Right? That's called a permutation. Now, what's the formula for this? It's this formula here. You have n objects, in this case, n runners, eight runners, n is 8, taken r at a time, 3 at a time, when order matters. In this case, it matters. Who's finishes first, second, and third, order matters. So the formula is n factorial. Now this, everybody familiar with a factorial, what a factorial is? Yes? So when I say 8 factorial, I mean 8 times 7 times 6 times 5, all the way down to 1. All those numbers are all multiplied together. 5 factorial is 5 times 4 times 3 times 2. So it's n factorial divided by n minus r factorial. Now, in the case we just did, with 8 runners, and we're looking at 3 positions, first, second, and third, r is 3. So this is 8 factorial divided by 8 minus 3 factorial, which is 5 factorial. So 8 factorial is 8 times 7 times 6 all the way down to 1. And 5 factorial is 5 times 4 times 3 times 2 all the way down to 1. And wouldn't you agree that 8 factorial is 8 times 7 times 6 times 5 factorial? And the denominator is 5 factorial, so they cancel out, and you're left with 8 times 7 times 6. All right? So intuitively, we knew it was 8 times 7 times 6, but the formula gives us the correct answer. And that's called a permutation. All right? The other possible way of counting is what's called combinations, where order does not matter. Order doesn't matter. So I'm going to give you an example from a deck of cards. All right? Suppose we have a 52 deck of cards, and 52 deck of cards consists of what? 13 different types of cards, 1 through 10, and then 3 face cards, right? The jack, the queen, and the king. So 13 different types of cards, and each one of those cards has 4 suits, right? 4 suits: clubs, spades, diamonds, hearts. So 13 times 4 is 52. That's why it's 52 cards. All right. Now, suppose out of those 52 cards, I want to create a hand of 5 cards. In other words, we're playing some game like poker. We have 5 cards. Each person who's participating in the game gets 5 cards. The question is, how many 5-card decks are there possible out of, or 5-card hands are there in a possible deck of 52 cards? Well, there are n is 52, and r is what? 5. It's the number of cards taken at a time. There's 5 cards. But the order does not matter. It doesn't matter if you have cards, if you pick 5 cards, and let's say they happen to be ace, 2, 3, 4, 5, right? Whatever suit they may be. It doesn't matter which one is chosen first, does it? You can change the position of the cards, and it doesn't matter. The game is played exactly the same way. So a combination is the number of combinations where order doesn't matter. So think about it. Think about permutations. Think about combinations. Permutations, order does matter. Combinations, it does not. So if I have a hand which has an ace, 2, 3, 4, 5 in it, right? And order doesn't matter, then it could be 5, 4, 3, 2, 1. It could be 1, 3, 5, 2, 4, right? You can think of all possible combinations that mean the same thing. But if order does matter, each one of those that I just mentioned have to be counted separately. So permutations are always a lot more counting than combinations are. And look at the formula for combinations. Now this formula here, this is a shorthand formula for it, where we put the number of objects in parentheses. We put the number of objects above, and then the number that we're taking at a time are below. This is not division, by the way. This is just a symbol of combinations. And it's equal to, it looks like permutations, where the numerator is n factorial and the denominator has n minus r factorial, but multiplied in the denominator is r factorial. The r factorial, what that does is it eliminates all those duplicate combinations. In other words, the 1, 2, 3, 4, 5 and the 5, 4, 3, 2, 1 are all considered it's considered the same in a combination. So all those duplicates get eliminated by dividing by r factorial, and we're left with the number of combinations. In many of the problems that we'll be dealing with, one of which is the binomial probability, we're going to be using combinations, right? So getting back to the deck of cards, if I wanted to know how many 5-hand decks there are in 52 cards, the answer would be 52 for N and 5 for R. And the answer, if you figure it out, and actually a graphing calculator, you can actually go into it, and there is functions in there where you can actually calculate the number of combinations. The answer is over 1 million. I think it's 1.4 or 1.5 million. It's somewhere in that vicinity. It's lots of possible combinations of hands, 5-card hands. Okay, over 1 million, maybe 2. I forget the exact number. It's a lot. So you're not going to sit there and count them. All right. This formula helps you count. That's the whole point. It's counting for large numbers of counting. Large numbers that we need to count. We use a formula instead of sitting there all day and wasting our time counting. So that's the answer. So if I was going to do the following, and I'm going to do, I don't want you to write this down, but I want you to just think about it just for a second. What if I wanted, now in poker, there's a hand called a full house. Full house, all right? Full house means 3 of a kind, which means 3 4s or 3 aces, whatever. That's what it means, 3 of a kind. And then the other 2 cards is 2 of a kind, okay? Of a different card, all right? So we could have a full house. An example would would be 3 5s and 2 7s. That would be a full house. If I wanted to calculate the probability of getting a full house, if I was given 5 cards, what's the probability of getting a full house? How would I figure it out? Well, the denominator is your sample space. And the sample space says there are how many hands? N is 52, R is 5, whatever that number is. And we put that into the denominator of what? Of our classical probability formula. In other words, this formula. That combination of 52 or 52 5 goes here in the denominator. What goes in the numerator? This is where it gets interesting. All right. And again, I'm not going to test you on this, but I want you to understand the concept of combinations because it'll help you later. In the numerator, it's all the possible outcomes of the event. What's the event? A full house. All right. Out of all the possible hands, full house. Now, 3 of a kind. How many different cards could be 3 of a kind? Well, there are 13 different types of cards, right? Ace all the way up to a king. So 13 possible 3 of a kinds. What is a 3 of a kind? Well, each type of card has 4 suits, right? And when I say 3 of a kind, I'm saying you're picking 3 of those suits out of the 4 suits. That's literally what you're doing. So 13 times combination where you have n is 4, and you're picking 3 out of 4 of those. It would be 4 for n and 3 for r. All right? 13 times that gives you the 3 of a kind. And then you have the 2 of a kind. The 2 of a kind, how many possible cards can you have for 2 of a kind? Well, if you already picked the card for 3 of a kind, how many cards are left?
12.
12. So it will be 12 times, and you're picking 2 cards out of the 4 suits. You're picking 2 suits out of the 4 suits. So it's n is 4 and r is 2. So putting all of that together, and remember we use the multiplication rule when we count. All right, this is a counting rule. We use multiplication. The answer is, for 3 of a kind, it would be 13 times 4 given 3. That's 4 for n and 3 for r, times 12 times 4, 2. Combination 4, 2. 4 for n, 2, 4. And that goes into the numerator. And that is what? That divided by 52, 5 in the denominator, 52 for n, 5 for the number of combinations, that gives you your answer. Now picture trying to do that, counting individual outcomes. It'd take you forever to figure that out. But this is what was determined. These formulas came out a long time ago, right, by these amateur mathematicians. But they worked, and they still work. Now, in a game of chance like poker, they say they have winning hands and they have losing hands. Why? Can you tell me in general, why is it the 4 of a kind, which is another possible calculation, is a winning hand over a full house? Why would you say it's a winning hand?
Because it's less likely to happen.
Less likely to happen. That's exactly right. And it's probability. That means the numerator of the probability formula has to be smaller than for a 4 of a kind than for a full house. Okay, it's more valuable. You can look at it that way. Something's more valuable means it's less likely to happen. Okay, and therefore it's considered a better hand, and that's why it works that way. The numerator of this classical approach becomes smaller for 4 of a kind. Now, how would you calculate 4 of a kind? Easy. There are 13 possible cards that could have 4. All 4 suits would have to show up, wouldn't they, out of 4? So n is 4 and r is 4, which happens to be 1. So it's literally 13 times, and what's left? The 12 cards, right, that have what? 1 out of 4, right? Only single ones for those. 13 there's 12 of those, right? 12 possibilities for having single cards, right? That's 4, 1. That if n is 4 and r is 1, that happens to be 4, by the way, when you calculate the factorials. So the answer is 13 times 12 times 4 in your numerator. And if you calculate that, you'll see that that probability is smaller than the probability of a full house. So that's how we work with combinations, okay? Combinations, we use the multiplication rule, but we also use that special notation of n given 4, all right? N given r. What I don't say, well, why is it 4? N given r, all right? That special notation, which we saw here, okay? This notation here, and this is the formula here. Now, let's actually jump into this a little bit. Let's actually go, I'm going to go to page 159 and look at some examples here. Examples 51, 53, 57, 58, 59, and that's it. All right. Let's go to the book. Actually, I have the book already open. So let's go to the book and just spend just a little time on this. All right, a little time on this. so that you understand how counting works. All right. In the book, they of course go through it, but in general, fundamental of counting is following. If an event happens m different ways, all right, m different ways, such as, for example, if you have 8 runners and we want to know how many ways can you have a first place winner, and there's 8 ways, right? 8 different people could end up in first place, all right? And there's n ways in which a second event can occur. The number of possibilities is what? And by the way, this notation is really weird in the book here. I would ignore this notation. I've never seen this before. It has a U and then has these dots above it. I don't know where they got that from. I haven't never seen it before. It should be that upside down U, which means intersect, M and N. In other words, it's M times N. We multiply, right? I'll give you an example. You go to a car lot. There are 4 types of cars in the car lot. All right, there's Toyota, there's let's say Toyota Camry, there's Honda Civic, there's a Hyundai there, there's a Chevy there. All right, there's 4 different types of car, and then there's 3 types of colors of car that you can choose from. How many different combinations of cars are there? There's 4 times 3 or 12, right? You could have 3 colors of Hondas, you could have 3 colors of Toyotas, like that. So you multiply. The principle of counting is also called the principle of multiplication, which is simply m times n. All right. And I just, again, I don't like the notation. They tend to change the notation in this book. If it were up to me, I'd find another book to teach all of this. But because here they say m times n, and then suddenly down here they say, all right, I'm going to call it n1 times n2. It's like, all right, I'm already confused, right? You're already confused. It's like, what is it with this notation? All right. And then if you have k, and what do we know? That these are independent, right, of one another. The type of car and the color of the car have nothing to do with each other. So we simply multiply the number of times the first event occurs times the second event. If there's more than 2 events, we keep multiplying. That's what they're saying down here. If there's k independent events occurring in this case in n different ways, it's n to the k. Again, this is very confusing, terrible notation. And I didn't write this book, by the way, so don't blame it on me. Another example, let's say, for example, I mean, they have a license plate here as an example. This is a decent example. Suppose you have a state license plate that has 6 different numbers or letters. All 26 letters and 10 digits are available for each of the 6 numbers. All right. So how many different letters and numbers there are there? There's 36 of them, right? So for each of the 6 positions or 6 positions of the license plate, there are 36 possible numbers or letters that you can have. And because each of those positions have the same numbers or letters, it's 36 times 36 6 times, or 36 to the 6th power. All right, which in this case is over 2.1 billion possible license plates. Okay, you put blank spaces in there, that's 37. Again, I don't know, if I was reading this for the first time, I would be thoroughly confused and wanting to cry for mommy. All right, literally. All right, now, a really good example, however, would be a combination lock. We've dealt with those, right? Or an alarm, something with an alarm, right? You push some buttons and then you turn the alarm off. All right, let's do an example of that one. Suppose we have a 4-digit code for an alarm. We just type in 4 digits, and let's say the first digit can be any number from 1 to 9, but not 0. okay? The second digit could be any number from 0 to 9. The third digit could be any number from 0 to 9. And the fourth digit can be any number from 0 to 9. How many different combinations can you have of, and that's a bad word to use, it's because it really has to do with permutations. But how many different possible lock combinations can you have? Well, the first position is 9, right? From 1 to 9. But the other three positions are from 0 to 9, which is 10. So it's 9 times 10 times 10 times 10, which is 9,000. So in that case, there are 9,000 possible lock combinations. The one that you pick is one out of the 9,000. All right, so it's kind of hard to, unless you have some technique that a burglar can figure it out, it's pretty hard to figure out which one of those 9,000 you've picked, okay? But that's how multiplication works in counting. Now, the permutations and combinations are just special cases of that, where each position for permutations changes in a very orderly way. In other words, we start at 9, and then we go down to 8, we go down to 7, and we multiply all those numbers out. All right, you see what I'm saying? As opposed to the combination example I just gave you, where the answer is 9 times 10 times 10 times 10. For a permutation, where we're like for a first place finish, it would be, the 8 runners were running, it would be 8 times 7 times 6. In other words, the numbers decrease by 1 as you multiply them. All right, so that's a subset of this counting principle, the permutations. And of course, a further subset would be combinations. All right, so you get the idea? We're simply just counting, and we're using this counting principle that I'm just talking about here. Okay. All right. And again, you can read through this, but I hope you know that, and then they go through here, the idea of what a factorial is, where 5 factorial would be 5 times 4 times 3 times 2 times 1. 3 factorial would be 3 times 2 times 1. And as I said a minute ago, you could also say that this factorial, 5 factorial, could be written as 5 times 4 times 3 factorial. One way of writing it, right? Because 3 factorial is what? 3 times 2 times 1. We could write 5 factorial as 5 times what? 4 factorial. We could say that 5 factorial is 5 times 4 times 3 times 2 factorial. All right. I want you to feel that this is an easy concept for you to craft, the idea of a factorial. So that's called the factorial rule of counting. All right. Notice that 0 factorial means what? 1 is equal to 1. 0 factorial is equal to 1. Okay. Permutations, we talked about those. All right. They show you how it works. Here's the formula. Then, of course, we have combinations is next. They gave you the formula right here. An example where order does not matter. Okay. You could look through these examples. Now, let's actually look through examples in book here, the one at the end of the chapter. Let's just see if we feel comfortable with these examples. All right. Hold on one second here. Let's see. All right. Give me a second here. All right, number 51. That's the one we're going to start off with first. This one right here. This is similar to the racing example I was telling you before. It says a committee consists of 8 members, each of whom may or may not show up for the next meeting. Assuming that the members will be making independent decisions on whether or not to attend, how many different possibilities exist for the composition of the meeting? Now, one thing we have to assume here also, just to make sure it makes sense, is that they're sitting, let's say, in a Oh, does the sitting make a difference? Let me think about this for a minute. No, I guess it doesn't matter. So let's assume they're sitting at a rectangular table. And position number 1 is at the front of the table, all right? So out of the 8 members, how many can sit in the position number 1?
Eight.
8. Once that person sits there, position number 2, how many people can sit there? Once we have selected one of the 8 people to sit in position 1, how many people can sit in position number 2? 7.
7.
You can't say 8 because one of the people's already sitting in position 1. So this is a case of permutation. This is a permutation question, right? Except we're not choosing out of the 8 at all, are we? We're not choosing like 3 out of the 8 or 4 out of the 8. We're looking at all 8 positions. So this is strictly a factorial question, right? The answer is going to be 8 factorial. 8 times for the first position, 7 for the second position, all the way down to the last. Whoever's left is left with that last seat, right? You've all been in that situation. We walk into a room and there's only 1 seat left. You don't have any choices, right? You sit there. So it's 8 times 7 all the way down to 1, which is 8 factorial. And that's the answer to 5.51. 8 factorial. Okay.
Professor, are we talking about 5.51?
Yeah, it's on page 159 of the textbook.
I feel like it should be 2 to the 8.
Which one are you looking at? 5.51 with the committee member? Why 2 to the 8th?
Because every member has 2 choices. They can show up or absent, and then there are 8 members.
Okay. So you're saying that I misread this problem.
I feel like so.
All right. Oh, I see. You know what? I think you're right. You're right. You're right. So because you could have only 1 person showing up, right?
Or none of them.
Or none showing up. Each of the 8 people, either they show up or don't show up. Okay. So the answer is 2 to the 8th. That's what you're saying? 2 to the 8th. Well, let me think about that for a second. I actually misinterpreted the problem myself here. Actually, you know what? I'm looking at my solution and I must be sleepy because there is my answer. 2 to the 8th. So I apologize. It's actually in your notes, right?
Nice job, Han.
So Han, you're absolutely right. I actually wrote it down 2 to the 8th here. And so why did I say it the other way? I have no idea. So I must be very sleepy tonight. I read it incorrectly and I get a big X through my entire body. All right. So I am bad. I apologize for that. So yes, the answer is 2 to the 8th. All right. So let's go back to the book here. Are you seeing the book or are you seeing the answer here? Are you seeing the book?
Book.
All right. So the answer is 2 to the 8th because each of the 8 people have 2 possible, they can either show up or not be there. And you're absolutely right. The answer that I gave says, how many different ways can 8 people sit at a table? And I have no idea why I thought this was this question. So I am very sleepy and I appreciate you, Han, for correcting me there. Be bad. Obviously, I read it correctly on another day. 5.53 is the next one. In advertising her oceanfront cottage for summer rental, a property owner can specify 1, whether or not pets are permitted, 2, whether the rent will be $700, $900, or $1,200 per week, 3, whether or not children under 10 are allowed, and 4, whether the maximum stay is 1, 2, or 3 weeks. How many different versions of the ad can be generated? So what is your answer? I'm sure Han will get this correct. This one is,
That's
this one even I can get tonight. Even sleepy Professor Barish can figure this one out tonight. What's your answer, Han? Did you get an answer?
I got 36.
36, that's right. So it's simply the multiplication
got,
rule. No, go ahead,
36.
Han. You explain it because I certainly can't. Go ahead.
Oh my god. Oh,
I'm not very good at explaining tonight. Go ahead.
because in the first option, you got 2 options at the first
Right,
material,
right.
and 3 options for the second one, and 2 options for the third one, and 3 options for the fourth one.
Right.
So multiply them.
You multiply 2 times 3 times 2 times 3, which is 36. Now, you have to be careful with this rule that you don't add those amounts. You don't add. A case where people sometimes add would be, and I gave you this as an example before, if you roll a die twice, how many different combinations of numbers can you have, right? And many people answer 12. But the answer is not 12, is it? What's the answer?
36.
36, because you multiply, don't add. But that one, a lot of people fall in that trap. I see many, many people answer 12 because they think there's 12. Here, I think it's harder to add, right? You can't picture adding here. But in the case of rolling a die twice, how many different possible numbers, possible combinations of the first and the second die are there? And the answer would be 36. So you multiply even in that case. Then we're going to look at 57. How many different combinations are possible if 6 substitute workers are available to fill 3 openings created by employees planning to take vacation leave next week? But we'll have somebody other than Han answer. Mo, maybe, or Mo, I can't see you, I can't hear you, so.
Sorry, yeah, I'm still here. So
You're still there.
Workers, 3 openings.
So how many are there for that one?
I think 18 possible combinations.
Okay, 18, okay. And anybody else? Han or Steve? Mo answers 18.
I think it I could be wrong, but it could be 120.
120, okay. How about Han? What do you think?
Steve.
You agree with Steve? Okay. So how did you figure out 120?
So there are 6 substitute workers and there's 3 openings. So that would be, the first opening would be filled by one of 6 people, and then that person is gone. So the second would be filled by one of 5 people. So after that, you have 4 left, and the third position would be filled by one of 4 people. So 6 times 5 times 4 is 30 times 4, which is 120.
All right, so you're considering it a permutation question.
Oh, okay. No, okay, so that's wrong.
Does
so,
the order matter? Does it?
No, the order does not matter. That's
the
right.
order doesn't matter. So what is the answer then?
The answer is that number divided by 3 times 2 times 1. So 120 divided by 6, which would be 10. No. Wow.
I think you
20,
have the
right? 20.
20. I think you have that same thing virus going around, the memory virus that I have.
Yeah.
20 is the answer, yes. Because order doesn't matter, right? It doesn't
Right,
matter
right.
who is picked first, right? Yes, because they didn't mention it here, right? They didn't mention that the order mattered, so it doesn't. Let's look at 5.58. Roadside Museum has 25 exhibits, but enough space to display only 10 at a time. If the order of arrangement is considered, they're sort of telling you here, how many possibilities exist for the eventual display? Now, I don't want you to actually come up with the number. I want you to come up with an answer with factorials, numerator and denominator. So how would you do this? What would be your answer? Yes, go ahead, Steve. Steve, yeah.
I believe it would be 25 factorial divided by 10 factorial.
All right.
No, wait. Yes, that's my answer.
All right, Han or Mo, any other answers?
I got 25 factorial over 15 factorial.
All right, so we have 25 factorial divided by 15 factorial, 25 factorial divided by 10 factorial. Mo, do you,
I
do you have,
I agree with Han.
you're going to agree
Man,
with
I'm
Han?
not
How
on-
about you,
I'm not
Mo?
on the ball.
What's your feeling about it?
Yeah, Han as well. I agree with Han.
Yes, Han, you're the student of the day here for sure.
Yeah.
So correcting me and getting everything correct, that's absolutely right. 25 factorial. Remember, the denominator for a permutation is n minus r factorial.
Right.
So it's 25. So it's very easy to fall into that trap. You answer the question too fast, right? And the answer is 25 divided by 25 minus 10 factorial, which is 15 factorial. All right, and the same thing goes for, well, let's look at number 59. A sales representative has 35 customers throughout the state and is planning a trip during which 20 will be visited. And how many orders can the visits be made? Now they give you the idea here of how many orders. So order does matter, right? So what would be your answer in this case here?
I'm afraid of guessing the wrong answer again and thinking too quickly, but my answer would probably be 35 factorial over 15 factorial.
Right, and Han, do you agree with that?
Yes.
Yeah. All right. All right, and again, these numbers are huge, right? Enormous, right? When you're dealing with combinations or permutations, you're dealing with an enormous number possible. I mean, if you multiply these numbers out, you could get 10 to the 20th power, huge numbers, which even computers have trouble counting that high. So you get an idea of the difference between permutations and combinations. Combinations, again, we're going to be working more with those than permutations, but just remember that 5.57 is your combination question. 6 given 3, right? That's one way of writing it. 6, that with the parentheses, 6 in the top and 3 in the bottom. We know the answer to that is 20, right? Because the order does not matter. If the order does matter, the answer for 57 would have been 120 if order did matter. All right, so that's one of the questions you have to ask yourself, does order matter? Just like with the poker hands, order does not matter, right? In terms of the 3 of a kind or 2 of a kind or full house, order doesn't matter which order you get the cards. So we combinations in that case. All right, so again, I want you to feel comfortable with this idea of counting, especially these more advanced formulas for counting. I think we have a few more minutes, so I want to go back to looking at some additional problems, and I think on Thursday we'll finish up this chapter on probability. I think you've learned enough, but we'll go over some more problems, which again are posted. You have it, right? I believe I posted it already. If you go to page 142, your text, and let me see if I can go back here a little bit. Let's see if I can find the questions. Page 142. Second here, this is 5.3. So let me see if I can find 5.3. Right here. Okay. Uh-oh, session has expired. So unfortunately, I have to log in again. So let me log in. Plugging in the wrong one here. Sorry about that. Go back. Getting in. There we go. All right, hold on a minute. Let me unshare and go back to that. This is very annoying. Just doing this. All right, 1 minute. Could be Cengage's. Oh, here we go. There's some issue with Cengage. You're not seeing what I'm seeing, but all right. And so 5.3 here. There we go. This is what I want. All right. So let me share again with you guys. All right, can you see this now?
Yes.
All right. So 5.12 is the one I want you to look at. Following contingency table of frequencies is based on a 5-year study, blah, blah, blah. So if you're familiar with one of these tables, right? You've looked at them before. All right, columns and rows are identified by the letters A through C and D through E, D through G. So the rows are ages and the columns are blood alcohol levels, all right? And what is the first question here? For this table, identify any two events that are mutually exclusive. Mutually exclusive. Remember, mutually exclusive means the events cannot occur at the same time. Now, when you consider any event, it's pretty easy to find mutually exclusive events here. Can you tell me one that's mutually exclusive, or two events that are mutually exclusive? Any of these, what is it, 7 different categories could also be looked at, right? Any of them, any two of those. So go ahead.
You can't be in column D and column E at the same time?
Exactly, right? You're either one age or another. You can't be, 18 and 22 at the same time, right? Right, and so you could pick any of these combinations, right? Even these cells that are inside here are combinations of A and D, B and E and things like that, even they are mutually exclusive from one another. So pretty much the whole chart here. Now, let me ask you a question. Is the 155 here, is that mutually exclusive from the 142?
No.
No, because the 155 includes the 142, doesn't it? Yeah. So not all the pairings here would be mutually exclusive. Some pairings are not because they're part of a larger group, right? All right, B, or number 2. For this table, identify any 2 events that intersect.
So just like DNA or E and B, just any of the columns that go into each other on the X and Y axis?
Yeah, any of these 12 cells in here are intersections, aren't they? Like this number 7 is referring to the intersection of B and D. This number 47 is the intersection of A and G. All of these in here are called joint counts, and they're intersections of 2 different events, right? Okay. Good. I just want to make sure when you read a table, you know how to read it. All right, let's look at 13. Because 13, I think, is based off of that table. Using the table in exercise 5.12, we'll go back to it in a second. How many victims were in the category described by A and not A?
Everybody.
All right, Steve says everybody. Han and Mo, what do you
Agree.
think? What is that?
I agree.
You say
Yeah.
everybody too? How about Han? A
Yeah.
and
Han already
not
said.
A. Huh?
I was just, Han already said is all.
What did you say, Han?
I said it's all the people.
All right, Han and Steve and Mo. No, 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 no. And means intersect. A and not A intersect. They're mutually exclusive. What's the answer?
So A and D.
0. 0.
Got it. Man, I am not on the ball.
Hey, I've redeemed myself. Yay. I'm back to Professor Barish. All right, here we go. I had to redeem myself before we ended the call. All right, how about C or F? Let's go back to C or F.
87, 83.
83 for C or F. Okay. C is this column and F is this row here.
Oh, wait, no.
No, it's gotta be 159 plus 114 minus 77.
That's correct. And what is that?
I don't hang on. $196.
Right. That's correct. 196 is the answer. So remember, if you have, now these 2 events are not mutually exclusive, right? Because they
Right.
both share what? The 77, right? They both share the 77. The 114 and the 159 both share the 77. So we have to subtract one of them out when we add up the marginal totals. All right. How about not A and not G? Not A and not G.
Is it 147?
That's correct. Now, how did you get 147?
So I basically blanked out everything from column A and blanked out everything from row G. So that just leaves the values of row B that are 7, 8, and 8, and then column C 6, 41,
All right,
and 77.
okay. All right, how about number 4, B or not G?
Is it 372?
That's correct, 372. So tell me how you did that one.
First, I took the total of B, which is 30, and then I added to that everything that was not G, which is rows F, E, and D. So that's 114 plus 96 plus 155. And then I subtracted where those two groups intersected, which is the values 7, 8, and 8 in column B.
23, yeah, you subtracted 23, yeah. All right, good. And Han and Mo, are you okay with what Steve was doing there?
Mhm.
And I think we'll do a couple more and then we'll stop for the night. But I do want you guys to feel comfortable in doing this. Again, with the table, the same table. What is the probability that a randomly selected victim would have been at least 60 years old and have had a blood alcohol level of at least 0.10? At least 60 years old and had a blood alcohol level at least 1.
Is it 35?
Over what?
Over what? Over.
You can't say just 35. It's a probability. So you're selecting somebody at random. Random means from what?
Over
That's-
454.
Right. That's your survey. That's the sample, right? So sample total. Yes. Good. And then finally, this last one we'll do tonight is 5.15. Another table here. I think you could do on your own. It says the following table represents gas well completions during 1986 in North and South America. So the well was either dry or not dry, right? Dry meaning it doesn't have any gas, and not dry means it has gas. And North America and not North America is South America, all right? So there's these 4 cells in the middle here, and here's your marginal totals. So the first part A says to draw a Venn diagram. So you have options here, but I will show you, actually, if you look at the solutions, the PDF here. Did I post this PDF with the, I did, right? This
Chapter
PDF
5?
here, this one here. Did I post that one?
We didn't
Can you see it?
No, we can't see an answer sheet on the
Yeah, you
screen.
can still see the book.
All right. This, I mean, do you have this? Did I post it?
Yeah.
Right. So I do have the answers for this. Let me show you how we'll look at the solution. Right here. So N represents what? North America, right? North America, and this other box here represents what? Dry, right? So north and dry together, when they intersect, it's 14,131. That's the intersection of N and D. So n, of course, this is your marginal total for n. And right, the sum of these two numbers, 31,575 plus 14,131 gives you the total for n, right? And then 14,131 plus 404 gives you the total for D. What's left? Well, this here, this 31,575 is the intersection of what? N not D. This is the intersection of N and D. And this is the intersection of D, not N. Right? Should I say it again? One more time? The 31,575 is N and not D. 14,131 is N and D. And the 404 is D and not N. Bless you. What's
Thank you.
left? The other one, right? The other one. The fourth cell, joint cell, which is not N and not D. That's 2563. That goes outside of these two boxes. And if you add all of these together, you get what? You get the 48,673, which I call the universal set. All right, that's your sample space. I'm calling it U, your universal set. So all these four numbers add up to the grand total, right, which is 48,673. All right. Again, we'll stop in 1 minute. I just want to get through this problem here. And then, all right, so let's stop sharing. We'll go back to the book. That's your Venn diagram. That's one way. You can draw it a different way. And then you can identify these regions, right? Automatically with your Venn diagram. That's what we already did, right? All four of those regions correspond to numbers in here, right? N and D is what? The intersection of N and D is the 14,131. Not N and not D would be 2563. You see the intersection of this row and this column. You see how all four show up? Yeah. Right, and then finally, this last one, using the table, assume that one well has been selected at random from the 48,673. What is the probability that the well was drilled in North America and was dry? Well, you're selecting out of the total, and it's this cell right here, 14,131. You're selecting for your numerator from North America and dry. And then the second question, what's the probability that the well was drilled in South America and was not dry?
That'd be 2,563 over 48,673.
That's it. Yeah. And I'm going to ask one other question before we go. What if I selected a well from North America? What's the probability that it was dry?
14,131 out of 48,673. Oh, wait, sorry, just out of the North American wells. So sorry, that'd be 45,706.
That's correct.
Nice.
That's correct. So you see the difference between those two questions? If I select a well at random, I'm selecting it from the entire sample, 48,673. But if I say I'm selecting a well from North America, I'm automatically eliminating the South America ones. So my denominator and my probability will be 45,706. In the same way, if I said I selected a dry well at random, then your denominator is going to be 14,535. Okay? Get the idea?
Yep.
All right. So I hope this helped today. We'll just finish the problems next time in this chapter and we'll be done. I hope this was a good preparation. for probability. I think Han, you had mentioned that you struggled with probability before, but you certainly didn't struggle tonight with it. So do you feel more comfortable with it? You feel
Yeah,
better?
sure. Yeah.
Oh. All right, good. And everybody else is feeling good? Feeling
Mhm.
better? All right. So we'll finish up this section next time. All right, don't forget about the test. All right. Obviously, I'm not going to assign anything new for you to read or anything. The only thing we're going to be doing on Thursday is finishing up the problems that I picked for the handout. So please put your attention on the test. All right. Make sure you have good Wi-Fi for those 75 minutes. Make sure there's no one around to holler at you and interfere with your test. No dogs or people or cats. And again, and also the Wi-Fi. Make sure the Wi-Fi is working well. If it's not at that time, wait. But don't wait to the last minute to take the test, because if suddenly you have a family emergency and then the Wi-Fi is not working and the computer explodes, then it's not a good time to take it. All right, guys, so that's it for tonight. I'm going to stop sharing and I'll stop recording. Any questions?
No.
Good. If you do have any last second questions, anything you wanted to review from chapters 1 to 4, you can send me an email. All right. So I'm going to stop recording.